Here we are, folks. Glad to be back again. Let's see what we can do with confidence intervals. Remember the last time we talked about confidence intervals for the mean where the sigma or the standard deviation was known, but this time unknown. Similar, but different. So let's see how that goes. Confidence intervals for the mean, standard deviation unknown. One more time. I guess so we get it right, correct? All right, so this time, because we don't know the standard deviation, we're going to use the t-distribution. Actually, there's a story behind that. Maybe I'll tell you in class. It has to do with a brewery, actually. We'll get back to that at a certain time. So the goal is to be able to construct and interpret the confidence intervals for the mean when the standard deviation is not known. All right, this should look a little bit familiar. The only difference is instead of t, or instead of z, you're going to use t because the standard deviation is unknown. Z to t. Now the t distribution is very similar to the z, actually. Honestly, if you saw the two at different times, you would think the t distribution is the same thing as the z one. It is bell-shaped and so on. We've got a list of the characteristics of that t distribution. But notice in particular that this looks very much like the one where we did know the standard deviation. Remember, the other one was z equals x bar minus mu over the standard deviation divided by the square root of n. Not much different. The only difference is that we don't know the standard deviation because, oops, sorry, I made a mistake. This should have been sigma because for the z, you actually know the standard deviation. Up here for the t, we don't know it. And our best shot is to use the standard deviation for our sample. We hope it's close. Next, the critical values, just like we had z sub c before when we knew the standard deviation, now we use t sub z. Very, very much the same. So here are the properties. This looks familiar. So your question to yourself is, you don't want to ask it and look silly, right? Z? Isn't that the same thing? Well, t distribution, you're still thinking, why isn't that the z? It sounds the same. Next, the area under the curve is 1. You sure that isn't the z distribution? Okay, here's where it looks a little bit different. The tails, remember that if we draw the picture that I keep harping about, here are the two tails. The catch is the tails are thicker. What that means is the part down here is not quite as close to the x-axis or z-axis or t-axis as it would be for when we know the standard deviation. Thicker means there's a little bit more area between these two. Also, the standard deviation is different depending on the size of the sample. Remember that's n? And it's greater than 1. For z, it was equal to 1. For the t, not quite the same. Next, we have one other thing, a new parameter we haven't heard of before. It's called the degrees of freedom, but it's very simple. The degrees of freedom which is shortened to DF for degrees of freedom. All you need to do is take the sample size, subtract 1. Degrees of freedom. 1 less than the sample size. That's all there is to it. But it is a little bit different because it's a t distribution instead. Remember, it's a t distribution because we don't know the population standard deviation. Next, here's a picture. Now, if we're looking at sample sizes, here's one where the sample size is a 3. So it gave us a degree of freedom of 2. 3 minus 1 is 2. Notice that in this curve, we've got an extra distance between that and the x-axis, or actually the t-axis. This part right here is thicker than it was previously with the z distribution. Even when we go to a sample size of 6, which gives us a degree of freedom of 5, it's still not quite as close as it used to be. Here's the standard normal curve. It gets real close to that axis, horizontal axis, very quickly. With a t distribution, it takes its good old time getting close to that, what looks like an x-axis. Therefore, our t distribution is a little different. 3 similarities, 2 that aren't quite so the same. Now, with a z distribution, or when we knew the standard deviation, that was good, right? Now that we don't know it, we're going to use the critical value of Tc instead of Zc. We'll still have a confidence similar to what we had before, but now the sample size becomes even more important than before. So here's how you can do it on your calculator. And here we might have a little bit of a split calculator-wise. To get that T sub C requires some extra work. Now, some of the TI-84s make this easy. Some of the newer TI-84s, we're going back 10 to 15 years, some of them have something called inverse T, like this, INV capital T. The oldest TI-84s do not have that. Old TI-84, very few of you have that, or the TI-83 definitely doesn't have it either. If you're using one of those, what you need to do is find the T table in the back of your book. Another possibility is you could get on the internet, search for a T table, and print that out. And then learn how to use it. That shouldn't be too hard, but that'll give you these T values that you need, these T values. Now, if you don't, if you have one of the newer TI-84s or the TI-Inspire, and this is for the TI-84, newer ones. If you go to second distribution, remember that's where we found the normal CDF, normal PDF, and all the rest of those. Once you get there, if you select number 4 for the inverse T, and that's going backwards so you get the T value. Put the area in, put the degrees of freedom, and remember the degrees of freedom equals, oops, sorry, that's a typo, n minus 1. That's your degrees of freedom equals, excuse me, n minus 1. check this out. Make sure you know how to get that, and you'll be in good shape. If you need to, use a table. Learn how to get that T sub C. Next, here's a picture of what it looks like. Now this is a T distribution, and although this looks like a regular standard normal curve, if you used a microscope, you could tell that in the tails, it's not quite as close to this horizontal axis as the standard normal was. That's why it's a T distribution instead of a Z distribution. Now remember how your calculator works. Typically, your calculator quite often, even with the newer TI-84s, sometimes insists that any area that it calculates or uses starts with negative infinity and goes to a certain point for a Z value, or in this case for a T value. So if we want a 95% confidence, that 95% confidence, remember, is in the middle. That means between these two edges, we're sharing 5% of the area, which means over here we have an area of half of that, half of 5%, and the other half of the 5% is over here. Now what does that mean? What we need is what this area is, from negative infinity up to the T value we need. So you'll need to use 0.975 and not the 0.95, unless you have a calculator that says, you're talking about the center, right? And then you can do it directly. Otherwise, you'll have to make this adjustment. That's going back to the picture again. Draw the picture for confidence intervals. That number you get for the confidence is right in the middle. Split the difference from 1 to the two sides. So 95 here, 5% in both of these, divide by 2, and then add this part and this part together to find what you're going to put in the calculator for the area. And that needs to be to the left of T sub C, which is this one right here. So your TI-84 or something similar, and I think the TI-Inspire works basically the same way. You're still going to look for that inverse T and work it the same way with the same area. So you need that picture and use your wits, keep your wits about you. Next, for 14 degrees of freedom, remember this is n minus 1, and you want 95% of the area is in the middle. But remember, your calculator is going to need this to give you the 95% confidence. You get to 2.145. To make some steps, make sure first, or check, if you don't know the population standard deviation, but the sample is random, and either the population is normally distributed, in which case you're home free, or for your sample, if the sample size is greater than 30, you still can assume that everything is normally distributed. Second, find the sample statistics. What's the size of the sample, the mean of the sample, and the standard deviation of the sample. Get the degrees of freedom. Real easy. N minus 1. To do that, or to use that, get T sub C. And that T sub C you can find by using the TI-84's inverse T function or by using the T table. Using that t sub c, then use this formula, which should look familiar from the last chapter. Multiply that critical t value times the sample standard deviation divided by the square root of the sample size, and you'll get your margin of error, big E. Those big E's are added to and subtracted from the actual mean for the distribution. That gives you the interval E, or x bar minus E to x bar plus E. That's your confidence interval for whatever the percentage you need. So here's an example, and here's one way of working it. First of all, you need to take that 95% confidence interval. You need to get the critical value of t first. So you can use inverse t or your t table to get that value. That's t sub c. And you put it in this formula to get the margin of error. So you have 2.145, that's t sub c. This you found from your sample, and this is your sample size. Do the calculations, and you get about 5.36. Some of these slides say 5.3. They were using the table, that's why they're a little bit off. So what does the confidence interval look like? Subtract E, the 5.3, from the mean. Add it to the mean, and that's how you get your confidence interval. Remember, the mean we had originally was 162. So we add the 5.3 to it, subtracted the 5.3 from it, and there's our confidence interval. So that means if we did this a lot of times and got confidence intervals that hopefully are similar, 95% of the time the real mean would be somewhere here in the middle. 5% of the time your confidence interval does not include this, and you would have a frowny face if you even knew, because remember, you don't know what the mean is. Next, that's what it looks like on the number line. This is the x bar that you found. That's your point estimate. You add E to it to get the right side, subtract E from it to get the left side of your confidence interval, and there you go, 156.7 to 167.3 is your confidence interval at a 95% confidence. If you change that confidence level, you're going to have a different confidence interval too. So here's some good wording. You would do well to write down that sentence. So hit pause, write it down. With 95% confidence, you can say the mean temperature, because you don't know it, of the coffee sold is between 156.7 degrees and 167.3 degrees. That is proper wording. So get that down. The wording is important. Now, how do you do this in the calculator? Well, you will be pleasantly surprised to see how we can do it this way. So, grab your TI-84. TI-Nspire will be very similar, so you can follow the directions even though they aren't exactly the same. And this number over here probably will be different. So hit the stat key, cursor back to get the tests menu, hit 7 for a Z interval, and that is a typo. It should be 8 because you want a t interval, right? There you go. We're fixed. Once you're there, at the top of your page, there's going to be a section right about there that gives you an option of either using data in one of your lists or stats that someone has given you or you've collected. Change it to stats, and then just below it, put in 10 for the standard deviation, which in this case would be S. My typo, I admit it. Put the 162 in for the sample mean. Put 16 for the sample size. Put the confidence level in there. By the way, notice that in this one, you don't need to make the adjustment. Put the confidence level directly as 95%. When you hit calculate, you're going to get the right answer. So I need to fix slide 18. I just need to remind myself. So how would you do this one? You have 36 cars at a car dealership. You want to find the number of days each car sat on the lot before it was sold. So you get some information, and maybe the sales manager tells you the sample or average number of days, it's there almost 10 days before it's sold, typically. And there's a standard deviation on that of 2.39, but remember, that's the sample because we don't have it for the year or for 5 years or 10 years, in which case we'd have the population one most likely. You decide on a confidence level of 99%. Why 99% when it's usually 95%? Because this is very important. We want to make sure we can get those cars off the lot, because as long as they're on the lot, they're costing money. So we want 99% so we can be more sure of the answer we get. So here we go. The standard deviation is unknown. The sample is random. We're good there. The sample is nice and big. It's over 30. So we use the t distribution. Remember, we didn't know the standard deviation, so we're going to the t. Using n equals 36, we've got the mean of the sample, the standard deviation of the sample, the confidence level we want, degrees of freedom, which is just one less than the 36. And you can use the table if you need to. You can use your calculator. You can get the margin of error at the 99% confidence level. And that margin of error is 1.09 days. Remember, keep in mind we're talking about how long the cars are on the parking lot. So here's how we can get the confidence interval. Add that 1.09 to the sample mean, subtract it from it. That gives us our confidence interval at a 99% confidence. That's important, because if we change the confidence level, the confidence interval will be different as well. That's what our confidence interval looks like on the number line. And if we did this a lot of times, 99% of our confidence intervals would contain mu, but 1% of the time we'll be wrong. We don't want to be wrong too often. That's why the 99%. You can do it, use something called Stat Crunch. We don't have that. That would be an extra. It costs a little bit more, so it's trying to save you a few dollars by using your current calculators. And here we go with the wording. Hit pause, write down the wording, get familiar with the wording because that's how it should say. With 99% confidence, you can say the population mean number of days the car model sits on the dealership lot is between 8.66 and 10.84. It could be as low as 10.66, could be as high as 10.84. We don't know what the average is. And 99% of the time, this will be the interval that we're going to use to make our decisions. Now, here's the other way. The way I showed you just a little bit earlier. If you want to do the same problem using all technology, grab your TI-84, hit the Stat key, go left to hit the Tests submenu, hit 7 for we have to fix this one too. For the T interval. That's a reminder for both of us, isn't it? Make sure at the top of that menu you make sure you have stats, unless you have the actual data in one of the lists. This will be the sample standard deviation because we don't actually know it. Notice sample standard deviation. Then we'll put in the sample mean, the size of the sample, the confidence level we need, and we should get the same thing. A little bit of a wrap up here to remind you, this is a flow chart, sort of like what programmers use. How do you get from here to there? First of all, you check this. Do we have a normally distributed population? Or, if it isn't, is our sample size 30 or more? Either case, we're in good shape. You can go down this way. If you don't, there's nothing you could find out. You can't get a confidence interval. But if either of these is satisfied, we go down this path, and the next thing we check is sigma known? Is the population standard deviation known? Maybe from historical information. If it is, then we're going to work with Z, the Z distribution, the standard normal distribution. If it's not known, if this is unknown, we're going to go this way and we'll use the T distribution and degrees of freedom. Another example for us. 25 newly constructed houses. We've got a mean. We've got a population standard deviation. Notice that. Very important. That means we're going to use Z-scores, not T-scores. Normally distributed, good. Notice it was only 25, so it's a good thing it was normally distributed, because if it hadn't been, we would have been out of luck. We would have had to go back and make our sample big enough so that we have a normal distribution. Now, do you use the normal one, the T distribution, or neither? You want a 95% confidence level interval about the population mean construction cost, and why? Okay, first of all, is it normally distributed or n greater than or equal to 30? Yes. It told us it was normally distributed, so even though your sample is a little bit on the small side, you're still okay. You can use the standard one or the T distribution because it's normally distributed. Now, which one? Are we going to use the Z or are we going to use the T? And there's where we have the next question. Do we know the population standard deviation? Yes. So, we'll use the standard normal distribution. We'll be talking about Z-scores instead of T-scores. Just a little bit better. So, here's our question again. It's normally distributed. and go through the paperwork, so to speak. And sample of 25. Here's your mean from the sample. Here's your standard deviation from the sample. Oops, no, we do know the population, excuse me. Which one do you use? Well, that's it. I'll see you in class. Goodbye.